Learning objectives. In this chapter, the user will learn the following in detail. Naive string matching, Knuth-Morris-Pratt or KMP algorithm, Boyer-Moore algorithm, applications in bioinformatics. Applications in bioinformatics. Bioinformatics, the discipline which studies the computational problems arising from molecular biology, poses many interesting problems to the string searching community. We will describe two problems arising from bioinformatics, their preliminary solutions, and the more general problem that they possess. The first problem is searching for alpha helices in protein sequences. This particular instance of the search is based on matching of hydrophobicity or hydrophilicity. We find an algorithm which is linear in the sequence length for fixed helix length and is big O of n log n for any helix length. The second problem is on matching probabilistic sequences against sequences or against other probabilistic sequences. In both cases, we derive efficient formulas to compute scores according to a Markovian model of evolution. String searching problems in bioinformatics are normally posed in terms of returning a score as opposed to a binary answer. This is quite fundamental since most of the time these searching problems return the likelihood of a certain event. Consequently, we will assume that the common denominator for the problems described herein is that our hits are not binary yes or no, but rather return a score, and we will be searching for the highest scoring strings. The nature of the biological problems and the omnipresence of random perturbations quickly indicates that exact matches are never interesting. Furthermore, string searching problems are seldom a goal in themselves in bioinformatics. Usually, they are one of the many building blocks for other computations. Typically, the results of our searching goes into higher level processes like classification, structure prediction, multiple sequence alignments, or phylogenetic trees. It should also be pointed out that these are real problems which we encounter every day in our work with biologists and in the development of Darwin, a system for doing bioinformatics computations. Molecular biology information consists of sequences of DNA or RNA, 4 symbols, or sequences of amino acids, 20 symbols, normally called proteins. An example of a DNA sequence is shown here. An RNA sequence, messenger RNA, mRNA in this case, derived from the above, and the protein it encodes are shown below. An example of a protein or amino acid sequence is as follows. For computer scientists, the difference between DNA and RNA is that all the T's are replaced with U's. 3 consecutive bases of RNA properly synchronized are called a codon. We can assume that all forms of life use 20 amino acids, which are the components of all proteins and are also encoded in a single letter alphabet. The above sequence comes from the yeast, Saccharomyces cerevisiae genome. As we said before, we are scoring all of our hits with a scoring function. Typically, a scoring function has the form as shown in below, where S of I is the ith symbol in the sequence and L is the length of the pattern to be scored. Example for L equals 6. S1 equals F1 of M, I, V, N, N, T. S2 equals F2 of I, V, N, T, H, etc. Our searching problems can be described as finding the I values for which Si is largest. The above is too generic. Quite often we have scores which are of the form as shown below. Here R is a relatively simple reduction function. We use the terminology from relational databases, where a reduction function is a function that maps a set of elements into a single one, for example plus, max, etc. Example is shown in below figure. An important class of scoring functions are derived from probabilities, sometimes from likelihoods. If probability of event I denotes the probability of a certain event, for example the probability that the sequence is homologous to some pattern, then SI equals minus log probability of event I is a very practical and reasonable scoring function. There are many good reasons to use the above, among others. It provides a sound foundation to the score. Scoring of independent events results in the sum of the scores. This is a very desirable property for building other algorithms on top of scores, most notably dynamic programming algorithms. It allows to relate or compare scores obtained from different sources. In this context, it makes perfect sense to search for the highest scoring sequences and not just a single one or a single target score. Identifying alpha helices. The first problem is related to the identification of alpha helices in protein sequences. A similar but simpler problem arises with the identification of beta strands. We will concentrate on the first problem. An alpha helix is a unit of secondary structure of proteins, found in many proteins. About 3/4 of the proteins contain alpha helices. Recognition of alpha helices from the primary structure sequence of amino acids is usually called secondary structure prediction and is a very important and active area of research. An alpha helix is a helical structure which rotates 100 degrees with every amino acid. Its existence and stability is normally due to its hydrogen, weak bondings, and its surroundings. A helix normally does not stand by itself. In particular, many helices find themselves in the interface between the inner and outer part of the protein. This information is very useful to search or confirm helices, as one side of the helix is hydrophobic, the inner side, and the other is hydrophilic, the outer side, typically exposed to water. The inner part of a protein almost always hydrophobic, while the protein normally is water soluble, hence the outer part should be hydrophilic. Hydrophobicity is the property of disliking water, like oily substances. Each amino acid has an index of hydrophobicity. Hydrophobicity indices range from -1 to 1 or some other similar range which can be mapped to -1 up to +1. An index of 1 means that the amino acid is highly hydrophobic, and index of -1 means it is highly hydrophilic, likes water. Hence, a natural score for a sequence of L amino acids starting at position J is the internal product as shown in below, where theta is the phase angle of the helix with respect to the inner or outer limit, and Hi is the hydrophobicity index of amino acid I. The score for each J and L depends on theta, so we first have to find the best theta for each position J. Matching profiles or probabilistic sequences. A probabilistic sequence, also called profile, is a sequence which is defined by a probability vectors for each position. It is interpreted as each position having several choices, all the characters which have a corresponding non-zero probability. This is a natural generalization of matching certain regular expressions, where we additionally want to find the most likely match with highest likelihood, of all possible ones. The following figure shows an example of a profile or probabilistic sequence of length 4 for DNA. Notice that the second and fourth positions are equivalent to a deterministic match and that the third position is equivalent to a don't care match. 4 main uses of probabilistic sequences. Probabilistic ancestral sequences. This can be used to build the root or other internal nodes of phylogenetic trees. It is the best method to obtain information about the ancestral sequence. 8,11. Multiple sequence alignments. Multiple sequence alignments can be constructed by aligning groups of sequences against groups of sequences using dynamic programming over the probabilistic sequences representing each group. 7,14. Patterns or motifs. An excellent example of patterns and motifs is the ProCyte 2,5,13 database. ProCyte is a database of protein families and domains. It consists of biologically significant sites, patterns, and profiles that help to reliably identify protein families and functional sites. Profiles. It is a common practice to summarize the common parts of a set of related sequences by a profile, probabilistic sequence, which is then used to search an entire database. This method detects more distant homologies than by searching with sequences alone. Matching a given sequence against a probabilistic sequence. Scoring an amino acid against a probabilistic sequence is not completely trivial if it is done according to the standard Markovian model of evolution. The first approach of taking the expected value of the score for each entry is not correct. A much better score is given by the logarithm of the quotient between the probability of being homologous, that is coming from a common ancestor, divided the probability of being matched by chance, null hypothesis. Let V be the probability vector to be scored against amino acid A, and D1 is the distance between X and V, and D2 is the distance between X and A, as shown in this figure. The quotient of probabilities is shown in below figure. The probability is summed over all possible values of the ancestor of X and all possible values of the probabilistic position of I. We will develop the simplification of this formula in detail, as there are several important steps in its computation. Notice that the event of having a common ancestor is the product of three probabilities, which are well visualized in this figure. First, we have the natural frequency of the root fx, then the probability that x mutates to one of the v's, and finally that x independently of the previous mutates to an a. According to the Markovian model of evolution, the probability of a mutation from A to B is given by probability of A implies B equals m power d into BA, where m is a unit, 1 PAM unit, mutation matrix, and d is the distance in PAM units between A and B. Hint: point accepted mutation. 1 PAM equals 1 mutation per 100 amino acid. PAM units used to measure the amount of evolutionary distance between two amino acid sequences. We place parentheses around m power d to emphasize that the powering is done before the selection of the subindices. A 1 PAM matrix means that the amount of expected mutation is 1% of the positions, or in mathematical terms, summation of I equals 1 to 20, 1 minus MII equals 0.01. M power d is the mutation matrix corresponding to a d-PAM distance. The mutation matrices have two additional mathematical properties. 1. The natural frequencies vector f is an eigenvector of m with eigenvalue 1. Mf equals f. In simple terms, the natural frequencies are not altered by a mutation event. And 2. A symmetry property arising from the construction of these matrices, Fa into MBA equals Fb into MAB. With this notation, the probabilities quotient becomes probability of common ancestor over probability of random occurrence equals summation x summation I fx of m power d1 ix vi m power d2 into ax over fv into fa. Using the symmetry relation on the second m and Inverting the summation, we obtain the result as follows, which finally becomes S of v, a equals 10 log 10 UA by FV, where U equals V power T into M power D1 plus D2. Observe that the final score does not depend on D1 and D2 individually, but only on their sum. This is a well-known phenomenon which indicates that what really matters is the distance between V and A and not where the root is placed. S of v, x can be pre-computed for every amino acid x at the cost of a matrix vector multiplication, computing U, and the same amount of space as V itself. With this pre-computation, scoring each position is big O of 1 and extremely efficient. Matching two probabilistic sequences. Scoring a probabilistic sequence against another is done following similar lines. This figure describes the situation of scoring one particular position against another. This time we have a triple sum over the unknown ancestor and over each of the two probabilistic descendants. That is, probability of common ancestor over probability of random occurrence equals triple summation of xij fx, probability of x implies I into vi into probability of x implies j into wj over fv into fw. Using the same technique as before, we obtain the result as follows, where v star equals v by fv can be pre-computed for the first sequence. W star equals m power d1 plus d2 into f over fw can be pre-computed for the second sequence, and f is the diagonal matrix containing the natural frequencies, that is, fii equals fj. Multiplying a vector by f can be done in linear time, so this multiplication does not affect the complexity. The pre-computation takes as much space as the probabilistic sequences and a matrix vector multiplication for each position w. Clearly, we choose w to be in the shortest of the two probabilistic sequences. The computation of the score, besides pre-computation, requires an internal product of two vectors of size 4 or 20 number of symbols. This is quite efficient since the pre-computation is dwarfed by the matching phase. Boyer-Moore algorithm. Boyer and Moore (BM) algorithm finds the occurrences of P in S in a time in big O of n in the worst case. However, since the KMP algorithm examines every character of the string S at least once in the case when P is absent, it makes at least n comparisons. The BM algorithm, on the other hand, is often sublinear. It does not necessarily examine every character of S, and the number of comparisons carried out can be less than n. Furthermore, the BM algorithm tends to become more efficient as m, the number of characters in the pattern P. In the best case, the BM algorithm finds all the occurrences of P in S in a time in big O of m plus n by m. As with the KMP algorithm, we slide P along S from left to right, checking corresponding characters. The characters of P are checked from right to left after each movement of the pattern. Use two rules to decide how far we should move P after a mismatch. 1. If we have a mismatch, immediately after moving P, let C be the character opposite P of m. We know that C is not equal to P of m. If C appears elsewhere in the pattern, we slide the letter along in such a way as to align the last occurrence of C in the pattern with the character C in the target string. If C does not appear in the pattern, we align the letter just after the occurrence of C in the target string. Rule 2. If a certain number of characters at the end of P correspond to the characters in S, then we use this partial knowledge of S, just as in the KMP algorithm, to slide P along to a new position compatible with the information we possess. Example 1. Let S contains the string This is a delicate topic, and P contains a string cat. The target string and the pattern are initially aligned as follows. We examine P from right to left. There is an immediate mismatch in the position shown by the arrow. The character opposite P of M is I. Since the pattern does not include this character, we slide the pattern just to the right of the arrow. Examine P from right to left, and again there is an immediate mismatch, since I does not appear in the pattern. There is once again an immediate mismatch, but this time the character A that appears opposite P of M also appears in P. We slide P one place along to align the occurrences of the letter A and start checking again at the right hand end of P. Now, when we slide P along one position to align the A in the target string with the A in the pattern, P is correctly aligned. A final check, always from right to left, will confirm this. In this example, we have found P without ever using rule 2. We have made only 9 comparisons between a character of P and a character of S. To implement the algorithm, we need 2 arrays D1 of character set and D2 of 1 to M minus 1, the former to implement rule 1 and the latter for rule 2. The array D1 indexed by the character set we are using is easy to compute. For every character C as shown in below. This is the distance to move P according to rule 1 when we have an immediate mismatch. It is more complicated to compute D2. We shall not give the details here, but only an example. The interpretation of D2 is the following. After a mismatch at position I of the pattern, begin checking again at position M, that is at the right hand end of the pattern, and D2 of I characters further along S. Example, suppose the pattern is P equals ASSESSES. Suppose further that at some moment during our search for the string P in S, we have a mismatch in position P of 7. Since we always examine the characters of P from right to left, we know that starting at the position of the mismatch, the characters of S are XS, where X not equals E. The fact that X times of E does not rule out the possibility of aligning the S in P of 6 with the S we have found in S. It may therefore be possible to align P as follows. We start checking again at the end of P, that is 3 characters further on in S than the previous comparison, thus D2 of 7 equals 3. Similarly, suppose now that we have a mismatch at position P of 6. Starting from the position of the mismatch, the characters of S are XES, where X not equal to S. The fact that X not equal to S rules out the possibility of aligning the E and the S in P of 4 and P of 5 with the E and the S found in string S. It is therefore impossible to align P under these characters, and we must slide P all the way to the right under the characters of S that we have not yet examined. We start checking again at the end of P, that is 10 characters further on in S than the previous comparison, thus D2 of 6 equals 10. As a third instance, suppose we have a mismatch at position P of 4. Starting from the position of the mismatch, the characters of S are XSSES, where X not equal to E. In this case, it may be possible to align P with S by sliding it 3 places right. Now we start checking at the end of P 7 characters further on in S than the previous comparison, so D2 of 4 equals 7. For this example, we find as shown. We also have D1 of S equals 0, D1 of E equals 1, D1 of A equals 7, and D1 of any other character equals 8. Note that D1 of S has no significance because an immediate mismatch is impossible at a position where S contains the character S. BM algorithm, shown in below figure. It returns either the position of the first occurrence of P in S or else 0 if P is not a substring of S. Problem 1. In this algorithm, the choice between using rule 1 and rule 2 depends on the test J equals M. However, even if J less than M, it is possible that rule 1 might allow K to advance more than rule 2. Continuing from example 1, consider the following situation. The failure of the match between T and E is of the second kind, so K is increased by D2 of 7 equals 3 to obtain as follows. However, the fact that T does not appear in P should have allowed us to increase K directly by D1 of T equals 8 positions. Show that the algorithm is still correct if we replace as shown below. We define D2 of M equals 1 and D1 of P of M equals 0. This modification corresponds to the algorithm usually known by the name Boyer-Moore, although these authors also suggest other improvements. It is easy to see intuitively why the algorithm is often more efficient for longer patterns. For a character set of reasonable size and a pattern that is not too long, Di of C is equal to M for most characters C. Thus, we look at approximately one character out of every M in the target string. As long as M stays small compared to the size of the character set, the number of characters examined goes down as M goes up. Boyer and Moore give some empirical results. If the target string S is a text in English, about 20% of the characters are examined when M equals 6. When M equals 12, only 15% of the characters in S are examined. Knuth, Morris, Pratt or KMP algorithm. Knuth, Morris and Pratt discovered linear time string matching algorithm by following a tight analysis of the naive algorithm. This algorithm avoids computing the transition function delta altogether, and its matching time is big theta of n using just an auxiliary function pi, which we pre-compute from the pattern in time big theta of m and store in an array pi of 1 up to m. The array pi allows us to compute the transition function delta efficiently in an amortized sense on the fly as needed. For any state q equals 0, 1, it goes up to m and any character a belongs to sigma. The value pi of q contains the information need to compute delta of q, a, but that does not depend on a. Since the array pi has only m entries, whereas delta has big theta of m modulus of sigma entries, we save a factor of modulus of sigma in the pre-processing time by computing pi rather than delta. The prefix function for a pattern. The prefix function pi for a pattern encapsulates knowledge about how the pattern matches against shifts of itself. Consider the operation of the naive string matcher. The below figure shows a particular shift S of a template containing the pattern P equals A, B, A, B, A, C, A against a text T. For this example, Q equals 5 of the characters have matched successfully, but the sixth pattern character fails to match the corresponding text character. The information that Q characters have matched successfully determines the corresponding text characters. Knowing these Q text characters allows us to determine immediately that certain shifts are invalid. In the example of the figure, the shift S plus 1 is necessarily invalid. Since the first pattern character A would be aligned with a text character that we know does not match the first pattern character but does match the second pattern character B. The shift S dash equals s plus 2, shown in part B of the figure, as shown below. However, aligns the first 3 pattern characters with 3 text characters that must necessarily match. It is useful to know the answer to the following question. Given that pattern characters P of 1 to Q match the text characters T of S plus 1 to S plus Q, what is the least shift S dash greater than S, such that for some K less than Q, P of 1 up to K equals T of S dash plus 1 up to S dash plus K, where S dash plus K equals S plus Q. In other words, knowing that PQ, suffix of TS plus Q, we want the longest proper prefix PK of PQ that is also a suffix of TS plus Q. Add the difference Q minus K in the lengths of these prefixes of P to the shift S to arrive at our new shift S dash, so that S dash equals S plus Q minus K. In the best case, K equals 0, so that S dash equals S plus Q, and we immediately rule out shifts S plus 1 up to S plus Q minus 1. In any case, at the new shift S dash, we don't need to compare the first K characters of P with the corresponding characters of T. Pre-compute the necessary information by comparing the pattern against itself, as shown in this figure. Since T of S dash plus 1, it goes up to S dash plus K, is part of the known portion of the text. It is a suffix of the string PQ. Formalize the information that pre-compute as follows. Given a pattern P of 1 to M, give the prefix function for the pattern P is the function pi, that is 1 up to M implies 0, 1 up to M minus 1, such that pi of Q equals max of K, such that K less than Q and PK is a suffix of PQ. That is, pi of Q is the length of the longest prefix of P, that is a proper suffix of PQ. This figure gives the complete prefix function pi for the pattern AB, AB, ACA and Q equals 5. In this figure, the pi function for the given pattern, since pi of 5 equals 3, pi of 3 equals 1 and pi of 1 equals 0. By iterating pi, we obtain pi times of 5 equals the set 3, 1, 0. In this figure, slide the template containing the pattern P to the right and note when some prefix pk of P matches up with some proper suffix of P5. We get matches when k equals 3, 1 and 0. In this figure, the first row gives P and the dotted vertical line is drawn just after P5. Successive rows show all the shifts of P that cause some prefix pk of P to match some suffix of P5. Successfully matched characters are shown shaded. Vertical lines connect aligned matching characters. Thus, k such that k less than 5 and pk is a suffix of P5 equals the set 3, 1, 0. The pseudocode below gives the North-Morris-Pratt matching algorithm as the procedure KMP matcher. For the most part, the procedure follows from finite automaton matcher. KMP matcher calls the auxiliary procedure compute prefix function to compute pi. These two procedures have much in common because both match a string against the pattern P. KMP matcher matches the text T against P and compute prefix function matches P against itself. We begin with an analysis of the running times of these procedures. Proving these procedures correct will be more complicated. Compute prefix function procedure is shown in this figure. Running time analysis. The running time of compute prefix function is big theta of m, which we show by using the aggregate method of amortized analysis. The while loop of line 6 to 7 executes big O of m times altogether. We shall show that it makes at most m-1 iterations. We start by making some observations about k. First, line 4 starts k at 0, and the only way that k increases is by the increment operation in line 9, which executes at most once per iteration of the for loop of lines 5 to 10. Thus, the total increase in k is at most m-1. Second, since k less than q, upon entering the for loop and each iteration of the loop increments q, we always have k less than q. Therefore, the assignments in line 3 and 10 ensure that pi of q less than q for all q equals 1 up to m, which means that each iteration of the while loop decreases k. Third, k never becomes negative. Putting these facts together, we see that the total decrease in k from the while loop is bounded from above by the total increase in k over all iterations of the for loop, which is m-1. Thus, the while loop iterates at most m-1 times in all, and compute prefix function runs in time big theta of m. Correctness of the prefix function computation. The prefix function pi helps us simulate the transition function delta in a string matching automaton. But first, we need to prove that the procedure compute prefix function does indeed compute the prefix function correctly. In order to do so, we will need to find all prefixes pk that are proper suffixes of a given prefix pq. The value of pi of q gives us the longest prefix. By iterating the prefix function pi, we can indeed enumerate all the prefixes pk that are proper suffixes of pq. Let pi times of q equals pi of q, pi square of q. It goes up to pi power t of q, where pi power I q is defined in terms of functional iteration, so that pi power 0 of q equals q, and pi power I of q equals pi of pi power I minus 1 into q for I greater than or equals 1, and where the sequence in pi times of q stops upon reaching pi power t of q equals 0. In the procedure compute prefix function, at the start of each iteration of the for loop of lines 5 to 10, we have take k equals pi of q minus 1. This condition is enforced by lines 3 to 4 when the loop is first entered, and it remains true in each successive iteration because of line 10. Lines 6 to 9 adjust k so that it becomes the correct value of pi of q. The while loop of lines 6 to 7 searches through all values k belongs to pi times of q minus 1 until it finds a value of k for which p of k plus 1 equals p of q. At that point, k is the largest value in the set. If the while loop cannot find a k belongs to pi times of q minus 1 such that p of k plus 1 equals p of q, then k equals 0 at line 8. If p of 1 equals p of q, then we should set both k and k belongs to pi of q to 1. Otherwise, we should leave k alone and set pi of q to 0. Lines 8 to 10 set k and pi of q correctly in either case. This completes our proof of the correctness of compute prefix function. Correctness of the Knuth-Morris-Pratt algorithm. We can think of the procedure KMP matcher as a re-implemented version of the procedure finite automaton matcher, but using the prefix function pi to compute state transitions. Specifically, we shall prove that in the ith iteration of the for loops of both KMP matcher and finite automaton matcher, the state q has the same value when we test for equality with m. At line 10 in KMP matcher, and at line 5 in finite automaton matcher. KMP matcher simulates the behavior of finite automaton matcher. The correctness of KMP matcher follows from the correctness of finite automaton matcher. Before formally prove that KMP matcher correctly simulates finite automaton matcher, let's take a moment to understand how the prefix function pi replaces the delta transition function. When a string matching automaton is in state Q and it scans a character A equals T of I, it moves to a new state delta of Q, A. If A equals P of Q plus 1, A continues to match the pattern, then delta of Q, A equals Q plus 1. Otherwise, A is not equal to P of Q plus 1. A does not continue to match the pattern, and 0 less than or equal to delta of Q, A, which is less than or equals Q. In first case, when A continue to match, KMP matcher moves to state Q plus 1 without referring to the pi function. The while loop test in line 6 comes up false the first time, the test in line 8 comes up true, and line 9 increments Q. The pi function comes into play when the character A does not continue to match the pattern, so that the new state delta of Q, A is either Q or to the left of Q along the spine of the automaton. The while loop of line 6 to 7 in KMP matcher iterates through the states in pi times of Q, stopping either when it arrives in a state, say Q dash, such that a matches P of Q dash plus 1 or Q dash has gone all the way down to 0. If a matches P of Q dash plus 1, then line 9 sets the new state to Q dash plus 1, which should equal delta of Q, A for the simulation to work correctly. In other words, the new state delta of Q, A should be either state 0 or 1 greater than some state in pi times of Q. We are now ready to formally prove the correctness of the KMP algorithm by the following theorem. Theorem: if is the final state function of a string matching automaton for a given pattern P and T of 1 up to n is an input text for the automaton, then phi of Ti equals sigma of Ti for I equals 0, 1, it goes up to n. The proof is shown in this figure. That Q equals sigma of Ti after each time we execute line 4 of finite automaton matcher. Therefore, it suffices to show that the same property holds with regard to the for loop in KMP matcher. The proof proceeds by induction on the number of loop iterations. Initially, both procedures set Q to 0 as they enter their respective for loops for the first time. Consider iteration I of the for loop in KMP matcher and let Q dash be the state at the start of this loop iteration. By the inductive hypothesis, we have Q dash equals sigma of Ti minus 1. We need to show that Q equals sigma of Ti at line 10. Again, we shall handle line 12 in KMP algorithm separately. When we consider the character T of I, the longest prefix of P, that is a suffix of Ti, is either P, Q dash plus 1 or some prefix, not necessarily proper and possibly empty, of P, Q dash. Naive string matching. Text editing programs frequently need to find all occurrences of a pattern in the text. Typically, the text is a document being edited and the pattern searched for is a particular word supplied by the user. Efficient algorithm for this problem, called string matching, can greatly aid the responsive of the text editing program. Sample applications of string matching algorithms are search for particular patterns in DNA sequences. Internet search engines also use them to find web page relevant to queries, etc. Formalize the string matching problem as follows. Assume that the text is an array T of 1 to n of length n and that the pattern is an array P of 1 to m of length m less than or equals n. That the elements of P and T are characters drawn from a finite alphabet. For example, sigma equals the set 0, 1 or sigma equals the set A, B and it goes up to Z. The character arrays P and T are often called strings of characters. Example of the string matching problem shown in below figure, where we want to find all occurrences of the pattern P equals A, B, A in the text T equals A, B, C, A, B, A, B, C, A, B, A, C. The pattern occurs only once in the text at shift S equals 3, which we call a valid shift. A vertical line connects each character of the pattern to its matching character in the text, and all matched characters are shaded. Pattern P occurs with shift S in text T, or equivalently that pattern P occurs beginning at position S plus 1 in text T if 0 less than or equal to S and S less than or equal to n minus m, and T of S plus 1 it goes up to S plus m equals P of 1 to m. That is, if T of S plus j equals P of j for j lies between 1 and m. If P occurs with shift S in T, then we call S a valid shift. Otherwise, we call S an invalid shift. The string matching problem is the problem of finding all valid shifts with which a given pattern P occurs in a given text T. Except the naive brute force algorithm, each string matching algorithm performs some pre-processing based on the pattern and then finds all valid shifts. Call this later phase matching. The total running time of each algorithm is the sum of the pre-processing and matching times. Notation and terminology. The set of all finite length strings denoted by the symbol sigma star. Here, consider only finite length strings formed using characters from the alphabet sigma. The zero length empty string denoted by epsilon also belongs to sigma star. The length of a string x is denoted modulus of x. The concatenation of two strings x and y denoted xy has length modulus of x plus modulus of y and consists of the characters from x followed by the characters from y. A string w is a prefix of a string x denoted w is a prefix of x if x equals wy for some string y belongs to sigma star. Note that if w is a prefix of x, then modulus of w less than or equals modulus of x. Similarly, a string w is a suffix of a string x denoted w is a suffix of x is x equals yw for some y belongs to sigma star. As with the prefix w is a suffix of x implies modulus of w less than or equals modulus of x. For example, we have AB is a prefix of ABCCA and CCA is a suffix of ABCCA. The empty string epsilon is both a suffix and a prefix of every string. For any string x and y and any character a, we have x is a suffix of y if and only if xa is a suffix of ya. The naive string matching algorithm. The naive algorithm finds all valid shifts using a loop that checks the condition P of 1 to m equals T of s plus 1, it goes up to s plus m for each of the n minus m plus 1 possible values of s. Naive string matching algorithm is shown in this figure. The for loop of lines 3 to 5 considers each possible shift explicitly. The test in line 4 determines whether the current shift is valid. This test implicitly loops to check corresponding character positions until all positions match successfully or a mismatch is found. Line 5 prints out each valid shift S. Procedure naive string matcher takes time big O of n minus m plus 1 into m, and this bound is tight in the worst case. For example, consider the text string a power n, a string of n a's, and the pattern a power m. For each of the n minus m plus 1 possible values of the shift S, the implicit loop on line 4 to compare corresponding characters must execute m times to validate the shift. The worst case running time is thus big theta of n minus m plus 1 into m, which is big theta of n square if m equals floor of n by 2. Because it requires no pre-processing, naive string matchers, running time equals its matching time. The below figure shows the naive string matching procedure as sliding a template containing the pattern over the text, noting for which shifts all of the characters on the template equal the corresponding characters in the text. At shift S equals 0, we find the first letter of the pattern is matched with text, then check the subsequent letters of pattern. Here, finding a mismatch at shift S equals 1, so shift our pattern to the right by one letter. The algorithm finds one occurrence of the pattern at shift S equals 2. Part A to D shows 4 successive alignments tried by the naive string matcher. In each part, vertical lines connect corresponding regions found to match. Jagged line connect the first mismatched character found, if any. Naive string matcher is not an optimal procedure for this problem. In Knuth-Morris-Pratt algorithm is much better in the worst case. The naive string matcher is inefficient because it entirely ignores information gained about the text for one value of S when it considers other values of S. For example, if P equals AAAB and find that S equals 0 is valid, then none of the shifts 1, 2 or 3 are valid since T of 4 equals B. Conclusion. In this chapter, we have covered the following in detail: naive string matching, Knuth-Morris-Pratt algorithm, Boyer-Moore algorithm, and applications in bioinformatics.